The moment your automation begins touching more than a handful of systems, you start feeling the difference between pushing changes outward and letting systems pull changes inward, even if you don't have those words yet. Push provisioning is when a central controller actively reaches out to targets and applies configurations or installs components, like an instructor walking around the classroom adjusting every student's laptop. Pull provisioning is when each target system checks in, retrieves what it needs, and applies it locally, like students opening the same assignment portal and following the instructions at their desks. Both models can build correct environments, but they lead to different operational rhythms. And that rhythm matters because configuration chaos usually comes from inconsistent timing, inconsistent identity, and inconsistent sources of truth. Beginners often focus on which approach is easier to start, but practical operations focuses on what happens when something fails mid-run, when networks are flaky, and when you need to prove what was applied and why. If you choose intentionally, you get repeatability, safer reruns, and clearer governance. If you choose casually, you get a fleet that looks similar at a glance, but behaves differently when it matters most. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good way to compare push and pull is to focus on where decisions are made, because decision location determines how predictable your system will be. In push provisioning, the controller decides which targets to change and when to change them, and targets are mostly passive recipients. In pull provisioning, the target decides when it is ready to apply changes and requests instructions or packages at that time, and the controller is more like a source of policy than an active operator. That difference influences reliability because timing issues are one of the biggest sources of automation surprises. A push system can accidentally force changes onto a target that is not fully ready, such as a system that is rebooting, still initializing, or missing a dependency. A pull system can reduce that risk because the target can wait until it has reached a stable state before requesting updates. But it can also delay change if the target never checks in or checks in too slowly. Operationally, the question is whether you want the central system to enforce timing or whether you want the endpoints to self-time their compliance. Push provisioning usually feels more intuitive to beginners because it looks like the operator is in charge, and that can be comforting when you want quick, visible results. If you have a small number of systems on a stable network, pushing changes can be fast and easy to reason about because you can see the run start, see which targets succeeded, and immediately know which targets failed. That immediacy can be valuable in tightly controlled maintenance windows where you need to coordinate changes across multiple systems in a specific sequence. The risk is that push provisioning tends to amplify fragile assumptions, such as assuming every target is reachable right now and assuming each remote session will remain stable long enough to complete. When connectivity is intermittent, push provisioning can create partial application, where some systems are updated and others are not, which is a classic source of configuration chaos. The chaos is not only the mismatch itself, but the difficulty of explaining it later because you end up asking which subset got which version during which run. The safer push pattern is one that expects partial success and makes it easy to identify, retry, and converge. Pull provisioning often feels less direct because it shifts some control to the targets, but it can be more resilient in environments where reachability is limited or where inbound access is heavily restricted. Many environments prefer that targets initiate connections outward rather than allowing a controller to connect inward, because that reduces exposed management surfaces. Pull also aligns naturally with continuous enforcement, where systems regularly check for desired configuration and adjust themselves to match, which can reduce drift without requiring a human to schedule runs. The risk is that pull can hide problems if you don't design strong feedback, because a target might fail to apply a change repeatedly and you might not notice until the impact becomes visible. Another risk is uncontrolled timing, where too many targets pull a large update at once and overwhelm a shared dependency like a package repository or a configuration source. In practice, pull provisioning becomes automation-friendly when it includes clear reporting of compliance status and when check-in behavior is paced to avoid stampedes. When pull is designed well, it trades operator watches everything for system proves everything, which is often a better trade at scale. Configuration chaos usually begins with inconsistency, so a useful anchor is the idea of a single source of truth for desired configuration. Whether you push or pull, you need one place that defines what a correct system looks like, including versions, settings, and approved deviations. If push provisioning uses one set of templates for some environments and pull provisioning uses a different set for others, you create two truths, and two truths become arguments, confusion, and drift. Similarly, if different teams push from different laptops or different automation runners, you end up with subtle differences in what was actually applied, even if everyone believes they ran the same workflow. Pull provisioning can also create multiple truths if different targets point to different policy sources or if policy is updated without coordination. The operational discipline is to treat configuration definitions like shared infrastructure, versioned and reviewed, so that push and pull are simply delivery mechanisms for the same intent. When intent is stable, delivery method becomes a manageable choice rather than a source of inconsistency. That stability is what keeps your automation from fragmenting into untraceable one-offs. Another major driver of chaos is uncontrolled concurrency, meaning too much change happening at once without respect for dependencies and capacity. Push provisioning can create concurrency spikes when a controller starts many remote actions simultaneously, which can overload networks, target systems, and shared services. Pull provisioning can create concurrency spikes when thousands of systems check in at similar times, such as after a reboot storm or a scheduled check-in window. In both models, the operational outcome depends on pacing and coordination, not just correctness of the configuration content. A reliable approach includes deliberate throttling and staged rollout behavior so that changes ripple through the fleet rather than slamming it all at once. This matters for security too, because sudden load spikes can look like attacks, and defensive systems may respond by blocking traffic, which then breaks automation in confusing ways. When you manage concurrency intentionally, you reduce cascading failures and make your system's behavior easier to predict. Predictability is the antidote to chaos because it turns random outages into known limits and known schedules. Identity and authorization design is another place where push and pull differ in ways that directly affect safety and auditability. In push provisioning, the controller usually needs a way to authenticate to each target and perform actions with some level of privilege. If that identity is too powerful or too widely shared, a mistake or compromise can have fleet-wide impact in minutes. In pull provisioning, the targets authenticate to the central service, and the service decides what they are allowed to retrieve and apply, which can reduce the need for broad inbound administrative access. That doesn't remove risk, because now the policy source and distribution channel become critical assets, but it changes where you apply controls. A safe environment uses least privilege in either model, meaning the identity used for automation can do only what the automation should do and nothing more. It also relies on clear accountability, meaning you can trace which identity applied which changes to which systems at which times. When identity is sloppy, configuration chaos becomes a security incident waiting to happen because you can't tell whether inconsistency is a bug, a human shortcut, or malicious activity. Timing and readiness are especially important when you want to avoid chaos during provisioning and during ongoing updates. Push provisioning can fail when the controller treats reachable as ready, because reachability does not guarantee that services are initialized, dependencies are available, or the system is in a stable state. Pull provisioning can reduce that by letting the target apply changes after it reaches a known baseline, but it can still fail if the target's readiness signals are wrong or if the target begins applying changes while other critical initialization tasks are still running. The operational solution in both cases is to use evidence-based readiness, where the system confirms important prerequisites before making high-impact changes. This is not about adding complexity for its own sake. It's about avoiding half-applied configurations that behave unpredictably. Chaos is often the result of good intentions applied at the wrong time, such as updating a service while it's still starting or changing a dependency while clients are still connecting. When you design provisioning around readiness, you convert timing from a hidden hazard into an explicit condition that automation can reason about. State awareness and idempotency also shape how safe push and pull are when you rerun them after partial failure. Push provisioning often produces a clear run record from the controller's perspective, but it can be hard to know what truly happened on a target if the session dropped mid-change. Pull provisioning often produces a clearer target perspective because the agent or local process can record what it applied and can retry intelligently, but it can still get confused if it loses track of its own progress. In both cases, the safest automation is designed to converge, meaning reruns should move systems toward the intended configuration without duplicating side effects or corrupting settings. That requires actions that can safely be repeated and checks that prevent changes when no change is needed. When idempotency is weak, push failures lead to frantic manual cleanup, and pull failures lead to endless flapping where systems repeatedly try and fail. When idempotency is strong, the response becomes calm. Fix the root cause and rerun, knowing the rerun is a repair tool, not a dice roll. Reparable reruns are one of the clearest signs that your provisioning strategy is not creating chaos. Another subtle but common source of chaos is configuration drift created by emergency changes or by local modifications that bypass your provisioning model. Push provisioning can override emergency fixes unexpectedly if you rerun without understanding what changed, which can cause a second incident while you're trying to stabilize the first. Pull provisioning can also override emergency fixes if the target enforces desired state continuously, which can be surprising if responders expect changes to persist. The operational answer is not to abandon enforcement, but to build a controlled way to represent exceptions and to record them in the same system that defines desired configuration. When exceptions are explicit, responders can make a temporary change and also document the intention so the provisioning system doesn't fight them blindly. Chaos often comes from the tug-of-war between manual fixes and automated enforcement, where each side undoes the other. If you design the workflow so exceptions are part of the desired model, you turn a tug-of-war into a managed deviation with a planned resolution. That makes both security and reliability stronger because the system can tell the difference between intended variation and accidental drift. Environment types also influence whether push or pull feels more practical, and the safest approach often changes as you move from development to production. Development environments often benefit from push-style control because it can be quick to iterate and easy to run on demand when someone wants a fresh environment. Testing and staging environments often benefit from pull-style consistency because you want repeatable baselines and reduced drift so test results reflect real configuration rather than accidental differences. Production environments often use both. Push for carefully coordinated changes that must happen in a controlled window, and pull for continuous baseline enforcement and drift remediation that keeps the fleet aligned between major changes. The trick is to avoid having different definitions of desired state for each environment type unless the difference is intentional and documented. Chaos appears when development is loose, staging is sort of strict, and production is strict, because then bugs are really environment mismatches. When your environment types share a common configuration contract, push and pull become different ways to deliver the same contract rather than different contracts with different meanings. That alignment reduces surprise during promotion of changes. A practical way to avoid configuration chaos is to treat provisioning as a life cycle, not as a one-time creation event. Early in the life cycle, you may need initial bootstrapping, where a system gets the minimum it needs to become manageable, such as baseline networking, identity enrollment, and core policy enforcement. After that, you need steady-state maintenance, where the system keeps matching desired configuration and reports when it can't. Push provisioning often fits the bootstrapping phase when you need to ensure a particular sequence occurs, while pull provisioning often fits the steady-state phase when you want continuous convergence. The chaos happens when you try to use one approach for everything without respecting what each phase demands. If you push everything forever, you risk brittle connectivity assumptions and oversized central control. If you pull everything from day one without a safe bootstrap, you risk unmanaged systems that never successfully enroll or never reach a compliant baseline. A lifecycle mindset helps you apply each model where it naturally provides the most stability. Stability comes from matching the method to the phase, not from forcing one method to solve every problem. Observability is the final piece that separates calm operations from chaotic operations, because you can't manage what you can't see. Push provisioning often gives you centralized run logs, which are great for understanding orchestration, sequencing, and which targets were contacted. Pull provisioning often gives you decentralized compliance signals, which are great for understanding steady-state posture across the fleet. In both models, you need clear answers to basic operational questions, such as which systems are aligned, which are drifting, which failed to update, and why. Chaos grows when updates happen, but nobody can prove what changed, or when failures happen, but nobody can see which step failed on which system. The safest provisioning designs treat reporting as part of the product, not as a nice-to-have after the deployment works. Reporting needs to be specific enough to support troubleshooting without forcing people to guess, and it needs to be consistent enough that teams can build runbooks around it. When observability is strong, push and pull become controllable strategies rather than mysterious forces. As you bring all of this together, the key insight is that push and pull provisioning are not rivals so much as different control shapes, each with strengths that can either stabilize or destabilize your environment. Push provisioning emphasizes centralized orchestration, immediate feedback, and explicit sequencing, but it can create fragility if it assumes perfect reachability and perfect timing. Pull provisioning emphasizes endpoint-driven convergence and resilience to certain network constraints, but it can hide failure and create load spikes if check-ins and reporting aren't designed carefully. Configuration chaos appears when you allow multiple sources of truth, uncontrolled concurrency, sloppy identities, and unclear exception handling, regardless of which model you use. The antidote is a consistent desired configuration contract, strong idempotency, deliberate pacing, and clear observability that proves what happened. Once those foundations are in place, you can choose push when you need tight coordination and choose pull when you need continuous enforcement without sacrificing stability. In practical operations, the smartest choice is the one that keeps behavior predictable on good days and reparable on bad days.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.